Find the maximum moment in kip feet. In this problem, three beams, AB, BC, and CD, are welded together with fixed connections at points A and D. A 15 kip point load acts horizontally at the halfway point along beam AB, and a continuous load of 4 kips per feet acts downward along beam BC. The dimensions of the structure are provided, and the Young's modulus times the area moment of inertia for each beam is constant. To solve this problem, we'll identify the loads given in the problem statement. Then, we'll draw out the shear diagram for each beam, and then draw out the moment diagram for each beam, and identify the largest moment in the structure. To do so, we'll use the slope deflection equation for fixed connections, where the moment at the near connection, Mn, equals 2 times the Young's modulus, E, times the area moment of inertia, I, divided by the length of member, Nf, times the quantity, 2 times the deflection angle of the near joint, theta n, plus the deflection angle at the far joint, theta f, plus 3 times the deflection slope, psi, all added to the fixed end moment at the near joint. Using the slope deflection method, counterclockwise moments are negative and clockwise moments are positive. If we sketch the exaggerated shape of the structure after it is deformed by the loading, as shown in red, we notice the deflection angle at the fixed connections A and D equals 0, and the deflection slope between joints B and C equals 0 as well, since the deflection slope equals the displacement tangential to the length of the member divided by the length of the member, and joints B and C are expected to be at the same elevation after the structure is deformed. Writing out the equation for the moment at joint A, we'll replace the subscript n for near with A, and the subscript f for far with B, and we'll assign the subscript AB to the moment, member length, deflection slope, and fixed end moment. From the problem statement, we know the length of member AB equals 12 feet. Since there is a fixed connection at joint A, theta A equals 0. The fixed end moment at joint A in beam AB equals the moment at joint A if both ends of beam AB were fixed connections, where fixed end moment AB equals the midspan point load P times the length of the beam LAB divided by 8. Since this moment is in the counterclockwise direction, it is negative, and equals negative 22.5 kip feet. Simplifying the equation, the moment AB equals 2EI divided by 12 feet times the quantity theta B plus 3 times psi AB minus 22.5 kip feet. Next, the moment BA is calculated and refers to beam AB again, but from joint B. The length is again 12 feet, theta A is again 0, but this time the fixed end moment is positive 22.5 kip feet. Moment BA equals 2EI divided by 12 feet times the quantity 2 theta B plus 3 psi BA plus 22.5 kip feet. Since slope deflection psi BA equals slope deflection psi AB, we can make the substitution in the equation for the moment BA. At this point, we've defined moments AB and BA in terms of theta B, theta C, and psi AB. Next, we'll determine moments BC, CB, CD, and DC in terms of theta B, theta C, and psi AB. Then we'll use the equations of force and moment equilibrium to solve for these three variables, and ultimately for the moments and forces in the structure. If we next solve for moment BC, we know the length is 15 feet, the slope deflection is 0, and we don't yet know the fixed end moment for beam BC. From standard tables, the fixed end moment for a continuously loaded beam across the entire length equals the continuous load, W, times the length of the beam, L, squared, divided by 12. Plugging in these values, the fixed end moment, BC, equals negative 75 kip feet. This makes moment BC equal to 2 EI divided by 15 feet times the quantity 2 theta B plus theta C minus 75 kip feet. Moment CB is similar, except it's 2 times theta C, 1 times theta B, and a positive 75 kip feet. Moments CD and DC are solved using the same general equation. And for these two moments, there is no fixed end moment term. Since psi CD and psi DC equal psi AB, this substitution is made. At this point, we have defined 6 moments in terms of variables theta B, theta C, and psi AB. If we set the sum of the moments around point B and set the value equal to 0, and then the moment BA plus moment BC must equal 0. Substituting in the variables for moment BA and moment BC, we can simplify the equation so it is in terms of theta B, theta C, and psi AB. We'll label this equation as equation 1. Next, if we sum the moments about joint C, moment CB and moment CD are substituted into the equation, and the equation is solved in terms of theta B, theta C, and psi AB. We'll label this equation as equation 2. Our last equilibrium will be the sum of the forces in the horizontal direction equal to 0. The horizontal force at point A plus the horizontal force at point D equals 15 kips. If we draw a free body diagram on beam AB and sum the moments about point B, we can solve for the horizontal force at point A, which equals 90 kip feet minus moment AB minus moment BA divided by 12 feet. To solve for the horizontal force at point D, a free body diagram is drawn for beam CD. The moments are summed about point C, and the value is set to 0. And the horizontal force at point D equals the negative of moment CD minus moment DC divided by 12. Returning to the horizontal force equation, if we plug in the values for the horizontal forces at points A and D and isolate the 4 moment variables, our equation becomes moment AB plus moment BA plus moment CD plus moment DC equals negative 90 kip feet. Next, we'll substitute the defined values for these 4 moments in terms of theta B, theta C, and psi AB. Once simplified, this equation will be our third and final equation needed to solve our linear system of 3 equations and 3 unknown variables. Solving the linear system, the values of theta B, theta C, and psi AB are determined. With these values, the moment at each joint can be calculated explicitly by plugging in these variables. For example, the value of theta B and psi AB are plugged into the equation for moment AB, which computes to negative 24.19 kip feet. Making this substitution for the other 5 moments are computed likewise and shown here. Next, the horizontal reaction forces at points A and D are determined by plugging in the moments for AB, BA, CD, DC, and the horizontal reaction forces at point A equals 5.56 kips, and the horizontal reaction force at point D equals 9.44 kips. Two last values that need to be calculated before sketching the shear and moment diagrams are the vertical reaction forces at point A and point D. To solve for these forces, a free body diagram of member BC is taken, and the moments BC and CB are shown, and the vertical reaction forces are translated upward. The moments are taken about joint B, set equal to 0, and the vertical reaction force at joint D is isolated. The continuous load, the beam length, and the moments are plugged in, and the vertical reaction force at point D equals 31.24 kips. And from vertical force equilibrium, the vertical reaction force at point A equals 28.76 kips. At this point, we know the reaction forces, the reaction moments, and the intermediate moments in joints B and C. Therefore, we're ready to begin constructing the shear and moment diagrams for each beam. If we begin with beam AB, draw out a free body diagram, and then add the horizontal load and reaction force, the shear profile along AB is drawn out. If we add moments AB and BA, we can sketch the moment diagram as well. Since the problem asks to find the maximum moment, we'll keep a running tab on the maximum moment, which is currently 9.17 kip feet. With beam AB solved, we'll next look at beam BC. Drawing out the free body diagram and adding the continuous loading and point forces, the shear profile for beam BC is sketched out. After adding the moments BC and CB, the moment profile is sketched as well, with the maximum moment at 55.92 kip feet, near the center of span BC. For beam CD, the horizontal reaction forces and end moments are added, and the shear and moment profiles are sketched. After sketching the shear and moment diagrams for all three beams, the maximum moment occurs in beam BC, which equals 55.92 kip feet. When reviewing the possible solutions, the answer is A.